Now we start the next topic of derivative, which is in logarithmic differentiation and derivative of parametric function. Exercise 1.3, question number 3. Question number 1 and question number 2 we see in the previous lecture. Now we start question number 3, and in this question is given that question is find dy upon dx if. Here the question first is under root x plus under root y is equals to under root a. The given function which is in the form of implicit function, and if we have to find derivative of implicit function, then we first differentiate with respect to x. If differentiate with respect to x, then we can take a derivative of every separate function which is in addition or subtraction form. Here under root a constant function, derivative of root x is 1 upon 2 root x, which was with respect to x. Again, secondly, we have to find derivative of root y, and the derivative of root y is 1 upon 2 root y. Y is considerable function, we can take again the derivative of dy by dx y. Root a is a constant function, derivative of constant function is 0. If we take 1 by 2 common from both terms, we can write 1 upon under root x plus 1 upon under root y. Dy upon dx is equals to 0. If we shift this 1 by 2 right side, then we can write 1 by 2 into 0 is 0. Hence 1 upon under root x plus 1 upon under root y into dy by dx is equals to 0. Now if we shift this 1 by root x right side, then we can write this positive term into negative form. We can write minus 1 upon under root x. This under root y is divisible by dy by dx. We can write this right side dy upon dx is equals to minus under root y upon under root x. Similarly, we can write dy upon dx is equals to minus under root of y by x, which is a required derivative of y dy by dx. Similarly, we can solve these examples. Root x plus y root y is equals to a root a. This root x means x raised to the power 1 by 2. Y root y means y raised to the power 1 by 2. And a root a means a raised to the power 1 by 2. If the base are equal, then by using rules of indices, we can write 1 plus 1 by 2. X raised to the power 1 by 2 is 1 plus 1 by 2 is 3 by 2. Plus y raised to the power 3 by 2 is equals to a raised to the power 3 by 2. If we differentiate with respect to x, then we can take again a derivative of x raised to the power 3 by 2 separate, plus derivative of y raised to the power 3 by 2, and the derivative of constant function which a raised to the power 3 by 2 is also 0. Here x raised to the power n is n into x raised to the power n minus 1. Here we can write it 3 by 2 into x raised to the power 3 by 2 minus 1 plus 3 by 2 into x y raised to the power 3 by 2 minus 1 into dy by dx is equals to 0. Here, if we take 3 by 2 common from both the terms, we can write x raised to the power 3 by 2 minus 1, which is 1 by 2, plus 3 by 2, we can write y raised to the power 1 by 2 into dy by dx is equals to 0. If we shift this 3 by 2 right side, then we can write 0 into 2 by 3 is 0. Also we can write this x raised to the power 1 by 2 is root x plus under root y dy by dx is equals to 0. If we shift right side to root x, we can write under root y dy by dx is equals to minus under root x. Hence we can write dy upon dx is equals to minus under root x upon under root y. That is, we can write this again minus under root of x by y, which is a required derivative of y dy upon dx. Again the given function x plus root xy plus y is equals to 1, which is in the form of implicit functions. Again we differentiate given function with respect to x. We can take a derivative of x plus again we can take a derivative of under root xy plus again we can take a derivative of y, and derivative of 1, which is constant function, is 0. Now derivative of x is 1 plus derivative of root xy is 1 upon 2 under root of xy, and we can take again the derivative of xy plus derivative of y, which is dy by dx, is equals to 0. After that, 1 plus 1 upon 2 under root of xy, and we can write u into v imply x into dy by dx plus y into derivative of x is 1 plus dy upon dx is equals to 0. 1 plus this 1 upon 2 root xy into x, we can write x upon 2 under root of xy into dy by dx plus y upon 2 under root of xy plus dy upon dx is equals to 0. But we have to find here dy by dx. If we cancel this x, we can write 1 plus 1 by 2 into under root of ex by y into dy by dx plus, if y cancel, 1 by 2 into under root of y by x plus dy by dx is equals to 0. If we find dy by dx, then we can take a common dy by dx from right this term, and another term we can shift right side. Hence we can write 1 by 2 under root of x by y plus 1 into dy by dx is equals to these terms minus 1 by 2 under root of y by x plus 1 converted into minus 1. If we shift this term right side, then we can write dy upon d. First we take cross product of both 1 under root x upon 2 root y plus 1 into dy by dx is equals to, again we can write this, minus under root y upon 2 root x minus 1. If we take cross product, we can write under root x plus 2 root y upon 2 root y dy by dx. Here minus under root y minus 2 under root x upon 2 root x. If we cancel these both terms, we can write here, if we take minus sign common from dy upon dx, here 2 is cancelled. We can write minus under root y into under root y plus 2 root x upon under root x as it is into under root x plus 2 root y, which is a required derivative of y dy upon dx. Again, the next example number 4 is x cube plus x square y plus xy square plus y cube is equals to 81. This is also in implicit form. If we differentiate with respect to x, then we can write the derivative of x cube, which is 3x square, plus we can apply here u into v rules. Derivative of x square into y is x square into dy by dx plus y into derivative of x square, plus again we can write here x into derivative of y square plus y square into derivative of x, plus we can write here derivative of y cube is equals to derivative of 81. Also here we can write derivative of x cube. We know that the derivative of x cube is 3x square plus x square as it is into dy by dx plus derivative of x square is 2x. We can write here 2x into y plus here derivative of y square is 2y. Here we can write 2xy into dy by dx plus derivative of x is 1. We can write here y square plus derivative of y cube is 3y square into dy by dx, and 81 is a constant function. We can write the derivative of 81, which is constant function, is 0. Here we have to find derivative of y with respect to x, means dy by dx. If we take dy by dx common from these three terms and another terms shift is right side, then we can write x square dy by dx plus 2xy dy by dx plus 3y square into dy by dx is equals to This 3x square converted into minus 3x square plus 2xy become minus 2xy and plus y square become minus y square. If we take dy by dx common from these three terms, we can write x square plus 2xy plus 3y square into dy by dx is equals to, if we take minus sign common from both three terms, we can write 3x square minus 2xy plus y square. Now dy upon dx is equals to minus 3x square plus 2xy plus y square upon x square plus 2xy plus 3y square, which is a required derivative of y, dy upon dx. Next one, which is again implicit form. If we take direct derivative of this term, then we can take a derivative by using u into v form. Again, derivative of tan inverse x, derivative of cot inverse x, for so lengthy. First, we know that x square into y square is equals to, if we take this tan inverse of under root x square plus y square right side, then we can write tan inverse of under root of x square plus y square plus cot inverse of under root of x square plus y square as it is. We know that the inverse rule, which is tan inverse theta plus cot inverse theta, is equals to pi by 2. If we substitute the value of tan inverse of under root x by x square plus y square, cot inverse of under root of x square plus y square, we can write it x square into y square is equals to pi by 2. Now if we differentiate given function with respect to x, then we can write by using u into v rules, x square into derivative of y square plus y square into derivative of x square is equals to derivative of pi by 2, which is a constant function, is 0. Now the derivative of y square is 2y, we can write is x square into 2y into dy by dx. Again we can write y square into derivative of x square is 2x is equals to 0. If we shift this term right side, we can write 2x square y into dy by dx is equals to minus 2xy square. Therefore, we can write dy upon dx is equals to minus 2xy square upon 2x square y. Here 2 is cancel, x cancel, y square y cancel. We can write here dy upon dx is equals to minus y upon x, which is a required derivative of the given function x square y square minus tan inverse of under root of x square plus y square is equals to cot inverse of under root of x square plus y square. Next example, which is example number 6, is x into e raised to the power y plus y into e to the power x is equals to 1, is also in the form of, we can, if we differentiate this implicit function, if we differentiate with respect to x, then we can write here the rules of u into v. Again here u into v, we can write here x into derivative of e to the power y plus e to the power y into derivative of x plus y into derivative of e to the power x plus e to the power x into derivative of y is equals to the constant function 1, which is a derivative, is 0. Again ex into e raised to the power I as it is, we can take derivative dy by dx plus e to the power x y as it is, derivative of x is 1 plus y into derivative of e to the power x is e to the power x plus e to the power x into derivative of y, which is dy by dx is equals to 0. If we take dy by dx common both this term, we can write here x e to the power y dy by dx plus e to the power x into dy by dx is equals to, if I take this term right side, we can write y into e to the power x minus e to the power y. Now take dy by dx common both terms, we can write x into e to the power y plus e to the power x into dy by dx is equals to, if we take minus sign common from this term, y e to the power x plus e to the power y. Next one, we can write dy by dx is equals to this term y e to the power x plus e to the power y, which is multiple term. We can take right side, then it divide to whole this term. It means that x into e to the power y plus e to the power x, which is the required derivative of y dy upon dx. function is in implicit form. Again we can differentiate given function with respect to x. Here we can take a separate derivative of e to the power x plus y, which is e to the power x plus y into again the derivative of x plus y by using chain rule. Here the derivative of cos of x minus y, which is minus sin of x minus y into again the derivative of x minus y. We can write here derivative of e to the power x plus y into derivative of x is 1 and y is dy by dx equals to minus sin of x minus y as it is. Here the derivative of x, which is 1 minus dy by dx. If we multiply this term with a bracket e to the power x plus y into 1 e to the power x plus y plus e to the power x plus y into dy by dx is equals to minus sin of x minus y minus minus plus sin of x minus y into dy by dx. If we take this term left side and the remaining terms are right side, we can write e to the power x plus y into dy by dx. This term are positive, it convert into negative sign minus sin of x minus y into dy by dx is equals to minus sin of x minus y as it is. This term minus e to the power x plus y. If we take dy by dx common, we can write e to the power x plus y minus sin of x minus y into dy by dx is equals to minus sin of x minus y plus e to the power x plus y. Now we can write dy upon dx is equals to minus sin of x minus y plus e to the power x plus y upon e to the power x plus y minus sin of x minus y, which is the required derivative of the given function dy upon dx. Example number 8 is cos of xy is equal to x plus y. If we differentiate with respect to x, then we can write derivative of cos of xy is equals to derivative of x plus derivative of y. Derivative of cos, which is minus sin of xy as it is, we can take again a derivative of x into y. Here derivative of x is 1 and derivative of y, which is dy by dx. Here we can apply derivative of u into v minus sin of xy into, we can write x into dy by dx plus y into derivative of x is 1 is equals to 1 plus dy upon dx. If we multiply this minus sin of xy into this term, we can write minus sin of xy into x dy upon dx minus y sin of xy is equals to 1 plus dy upon dx. If we shift this term right side, we can write minus x sin of xy into dy by dx minus dy by dx is equals to 1. This minus converted into plus y sin of xy. If we take dy by dx common both term, we can write minus in bracket x sin of xy plus 1 into dy by dx is equals to y sin of xy plus 1. This term is multiple for dy by dx. If we shift right side, then we can write dy upon dx is equals to minus sign as it is y sin of xy plus 1 upon x sin of xy plus 1, which is a required derivative of y dy upon dx. Example number 9 also is in implicit form. Here the function is in form of e to the power x minus y. We know that the definition of log, which is if y is equals to log x, then we can write x is equals to e raised to the power y. If we write this function e to the power y in form of log, then log x, then also we can write this term into e to the power x minus y is equals to log of x upon y. Now, if we differentiate given function with respect to x, then we can write derivative of e to the power x minus y, which is derivative of e to the power x minus y, and we take again a derivative of x minus y. Derivative of log of x upon y, which is 1 upon x upon y, into we can take again a derivative of x by y. After that, e to the power x minus y as it is, derivative of x is 1, derivative of y is dy by dx, is equals to, we can write 1 upon x y is equals to y by x. Here we can apply u upon v form, we can write y into derivative of x minus x into derivative of y upon y square. Here e to the power x minus y into 1 e to the power x minus y minus e to the power x minus y into dy by dx is equals to y cancel. We can write here 1 by x into 1 upon x into y into y, derivative of x is 1, minus x into dy upon dx. If we take this x into y right side, then we can write x into y, or we can write e to the power x minus y minus e to the power x minus y into dy by dx is equals to y into this y upon x minus y, xy, minus x upon xy into dy upon dx. Here y cancel, x cancel, we can write e to the power x minus y minus e to the power x minus y into dy by dx is equals to 1 by x minus 1 by y dy upon dx. If we shift this term dy by dx left side and this term is right side, we can write it minus converted into plus 1 upon y dy upon dx minus e to the power x minus y as it is into dy by dx is equals to 1 by x as it is. This e to the power x minus y is minus e to the power x minus y. If we take dy by dx common, we can write 1 upon y minus e to the power x minus y into dy by dx is equals to 1 by x minus e to the power x minus y. 1 into this 1 minus y into e to the power x minus y upon y into dy by dx is equals to 1 into this 1 minus x into e to the power x minus y upon x. Here, if we shift whole term right side, then y, you can write in numerator y into 1 minus x into e to the power x minus y upon x into 1 minus y into e to the power x minus y, which is a required derivative of the given function whole dy upon dx. Next one, x plus sin of x plus y is equals to y minus cos of x minus y. Again, if we differentiate with respect to x, then we can write derivative of x plus derivative of sin of x plus y, derivative of y minus derivative of cos of x minus y. Derivative of x is 1, derivative of sin of x plus y is cos of x plus y, and we take again a derivative of x plus y. Derivative of y, which is the dy upon dx, minus derivative of cos, which is sin, minus minus plus sin of x minus y, and we take again a derivative of x minus y. Here 1 plus cos of x plus y, and the derivative of x is 1 and y is dy by dx is equals to dy upon dx as it is plus sin of x minus y as it is into derivative of x is 1 minus dy by dx. If we multiply cos of x plus y is whole this bracket, then we can write 1 plus cos of x plus y into 1 cos of x plus y plus cos of x plus y into dy by dx is cos of x plus y dy by dx. Here dy by dx as it is plus sin of x minus y into 1 is sin of x minus y minus sin of x minus y into dy by dx. Now we take whole dy by dx term left side and the other remaining terms are right side. We can write cos of x plus y into dy by dx. After that, minus plus sin of x minus y into dy by dx. It become minus dy by dx is equals to sin of x minus y as it is. This cos of x plus y convert into minus cos of x plus y. Again this plus 1 convert into minus 1. If we take dy by dx common both three terms, we can write cos of x plus y plus sin of x minus y minus 1 into dy by dx is equals to sin of x minus y minus cos of x plus y minus 1. Then dy upon dx is equals to sin of x minus y minus cos of x plus y minus 1 upon cos of x plus y plus sin of x minus y minus 1, which is a required derivative of y dy upon dx. Next, which is question number 4, is show that dy upon dx is y by x, where a and p are constant. It is fixed that we have to find here dy by dx, and the answer which is y by x. Given function is a implicit function. It is a complicated function. If we find dy by dx, then first we take log both sides. If we taking log both sides, we can write it log of x raised to the power 7 y raised to the power 5 is equals to log of x plus y whole raised to the power 12. Here we can write log of x raised to the power 7 plus log of y raised to the power 5 is equals to 12 log of x plus y. Here again we can write 7 log x plus 5 log y is equals to 12 log of x plus y. We use the rules of logarithm here. First we apply log of m into n, which is log m plus log n here. After that, we again apply log of m raised to the power n, which is equal to log n log of m. Now if we differentiate the given function with respect to x, 7 into we can take a derivative of log x, 5 into we can take a derivative of log y, 12 into we can take a derivative of log of x plus y. It is clear that we have find dy by dx, and this term whole convert into y by x. The derivative of log x is 1 by x. Similarly, we can write derivative of log y is 1 by y into again a derivative of y, which is dy by dx. Here again we can write derivative of log of x plus y is 1 upon x plus y, and we can take again a derivative of x plus y. 7 into 1, which is 7 by x plus 5 by y dy by dx is equals to 12 into 1, 12 upon x plus y into derivative of x is 1 and y is dy by dx. Now 7 by x plus 5 by y into dy by dx as it is. Here 12 into 1, which is 12 upon x plus y plus 12 upon x plus y into dy by dx as it is. If we take whole this term left side, then we can write 5 upon y dy upon dx minus 12 upon x plus y into dy by dx is equals to 12 upon x plus y minus 7 upon x. Here we take dy by dx common, we can write 5 upon y minus 12 upon x plus y into dy by dx is equals to 12 upon x plus y minus 7 upon x. Now we take a cross product of this whole bracket, and here we can write 5 into x plus y, which is 5x plus 5y minus 12y upon y in bracket x plus y dy upon dx. Again, if we take cross product on the right side, we can write 12 into x, 12x minus 7x minus 7y upon x in bracket x plus y. X plus y common bracket, both sides we can cancel here. We know that 5x, 5y minus 12y minus 7y upon y into dy upon dx is equals to 12x minus 7x, which is 5x minus 7y upon as it is x. Here this 5x minus 7y, 5x minus 7y common bracket we get cancelled here. 1 upon y we can write dy upon dx is equals to 1 by x. If we shift this by right side, then we can write this divider by divide y, which is divide the whole terms dy by dx. We can write in numerator y upon x, which is a required proof, dy upon dx, hence proved. Again, it is clear that here we have to find dy by dx and the value of dy by dx, which is y by x. First we differentiate given function with respect to x. We have to show that dy by dx is equals to y by x. Given function is in the implicit form. If we take log both sides, then we can write taking log both sides, we can write log of x raised to the power p plus log of y raised to the power 4 is equals to log of x plus y whole raised to the power p plus 4. Here we use log of m into n is equals to log m plus log n. Again we know that log of m raised to the power n is n log m. If we apply this rule here, we can write p log x, p is constant function, 4 log y, 4 is again constant, p plus 4 into log of x plus y. Now if we differentiate with respect to x, then we can write p into derivative, p is constant, derivative of log x, 4 is constant, derivative of log y, p plus 4 is again constant, we can take a derivative of log of x plus y. We know that the derivative of log x is 1 by x, we can write here p by x, derivative of log y is 1 by y, 4 by y, dy upon dx, p plus 4 upon derivative of log of x plus y, which is 1 upon x plus y, we can take again a derivative of x plus y. Here p by x as it is 4 by y dy upon dx is equals to p plus 4 upon x plus y, derivative of x is 1 and y is dy by dx. Here p by x plus 4 by y dy by dx is equals to p plus 4 upon x plus y plus p plus 4 upon x plus y into dy by dx. This whole term we can take left side, means 4 by y into dy by dx minus p plus 4 upon x plus y into dy by dx is equals to p plus 4 upon x plus y minus p upon x. It is clear that we have to find dy by dx. If we take dy by dx common, we can write 4 upon y minus p plus 4 upon x plus y into dy by dx. We can take here x into p plus 4 upon x plus y minus p by x. Here, if we take cross product of both sides, we can write 4x plus 4y minus py minus 4y upon y in bracket x plus y dy upon dx. Here px plus 4x minus px minus py upon x in bracket x plus y. Here x plus y cancel. Here plus 4y minus 4y cancel. Here plus px minus px cancel. Remaining terms 4x minus py upon y dy upon dx is equals to 4x minus py upon x. Here both the brackets are similar. We can get cancelled. Remaining terms, which is 1 by y dy by dx is equals to 1 by x. If we take y's both right side, then we can write dy upon dx is equals to y by x, which is a required derivative of y dy upon dx. Here example number 3, sec of x raised to the power 5 plus y raised to the power 5 upon x raised to the power 5 minus y raised to the power 5 is equals to a square. We have to prove that here dy by dx is equals to y by x. Now, if we take this sec right side, then we can write x raised to the power 5 plus y raised to the power 5 upon x raised to the power 5 minus y raised to the power 5 is equals to sec inverse of a square. Here sec inverse a square is a constant term. We can say here k. We can write sec inverse of a square is k. Then x raised to the power 5 plus y raised to the power 5. This term shift right side, we can write x raised to the power 5 minus y raised to the power 5. Now if we multiply this k into x raised to the power 5 minus k into y raised to the power 5, which is x raised to the power 5 plus y raised to the power 5. We take terms of x left side, terms of y right side, we can write it. If this term we can take left side, we can write x raised to the power 5 minus k x raised to the power 5 minus k y raised to the power 5 plus become minus y raised to the power 5. Here we take x raised to the power 5 common, here we take y raised to the power 5 common. We can write 1 minus k into x raised to the power 5 is equals to minus in bracket 1 plus k into y raised to the power 5. If we take this term right side, we can write x raised to the power 5 upon y raised to the power 5 is equals to minus 1 plus k upon 1 minus k. Now if we differentiate with respect to x, or we can write here x raised to the power 5 x upon y whole raised to the power 5 is equals to minus 1 plus k upon 1 minus k. If we take fifth root, then we can write taking fifth root, we can write here x upon y is equals to fifth root of minus 1 plus k upon 1 minus k. Now if we differentiate with respect to x, then we can write y into derivative of x minus x into derivative of y upon y square, and the whole terms is constant for term. We can write its derivative is 0. 0 into y square is 0. We can write y into derivative of x is 1 minus x into dy by dx is equals to again 0. If we shift this term right side, we can write it x into dy by dx is equals to y. If we shift right side, x is multiple of dy by dx, then we can write in denominator divided dy upon dx is y by x, hence proved. Again we have to prove dy by dx is equals to y by x, and the given function is the tan inverse of 3x square minus 4y square upon 3x square plus 4y square is equals to a square. If we take this tan inverse right side, we can write here 3x square minus 4y square upon 3x square plus 4y square. This a square tan inverse become tan of a square. Again it is a constant function. We can say it k means constant. Here we can write 3x square minus 4y square, this term divided to whole term. If we take right side, this we can write k into 3x square plus 4y square. Again 3x square minus 4y square as it is 3kx square plus 4ky square. This x square right side we get 3x square minus 3kx square is equals to 4ky square minus plus 4y square. If we take x square and y square common both sides, we can write 3 minus 3k x square 4k plus 4 into y square. If we take y square right side, the left side x square upon y square is equals to 4k plus 4 upon 3 minus 3k. If we taking square root both sides, then we can write x upon y is equals to under root of 4k plus 4 upon 3 minus 3k. Now if we differentiate this term with respect to x, then we can write y into derivative of x minus x into derivative of y upon y square is equals to this whole terms are constant function and the derivative of constant function is 0. Y square become y 0. Y into derivative of x is 1 minus x into dy by dx. Again if we take this term right side, then we can write minus x into dy upon dx is equals to 0 minus y minus y. This term are multiple. If we shift right side, then we can write dy upon dx is equals to minus y upon minus x. Minus minus plus, we can write dy upon dx is equals to x upon y, which is a required proof. Hence we can write dy upon dx is y by x, hence proved. Again we have to prove here dy by dx is equals to y by x. If we shift this cos in our right side, we can write 7x raised to the power 4 plus 5y raised to the power 4 upon 7x raised to the power 4 minus 5y raised to the power 4 is equals to cos of tan inverse A. This function is a constant function. We can see it k. Now 7x raised to the power 4 plus y raised to the power 5y raised to the power 4 is equals to k into 7x raised to the power 4 minus 5y raised to the power 4. If we multiply this k bracket, we can write k 7k x raised to the power 4 minus 5k y raised to the power 4, 7x raised to the power 4 plus 5y raised to the power 4. If we shift this term right side, then we can write 7x raised to the power 4 minus 7k x raised to the power 4 is equals to minus 5k y raised to the power 4 minus 5y raised to the power 4. If we take x raised to the power 4 y raised to the power 4 common, we can write it 7 minus 7k x raised to the power 4 minus in bracket 5k minus 5 into y raised to the power 4. If we take y raised to the power 4 right side, then we can write x raised to the power 4 upon y raised to the power 4 is equals to minus 5k minus 5 upon 7 minus 7k. If we take fourth root both side, taking fourth root both side, we can write fourth root of x by y, x upon y is equals to fourth root of minus 5k minus 5 upon 7 minus 7k. Now if we differentiate with respect to x, by applying the rules of u upon v, we can write it y into derivative of x minus x into derivative of y upon y square is equals to derivative which is whole terms is constant 0. This y square becomes 0, then we can write it y into derivative of x is 1 minus x into dy by dx is equals to again 0. Y, this become x into dy by dx. If we take x into dy by dx is equals to, also we can write y. If we shift this x right side, then we can write dy upon dx is equals to y by x, which is a required proof of dy upon dx is y by x, hence proved.